Welcome to this lesson on essential C programming concepts. In this video, we're going to dive into how variables, assignments, and expressions work in the C language. These concepts are fundamental to every program you'll write. We'll begin with variables, named storage locations that hold data like x or numPeople. You give a variable a value using an assignment statement, such as x equals 5, which stores the value 5 in x. That value remains until you reassign the variable. Every assignment has a variable on the left and an expression on the right. The expression can be a literal like 5, another variable, or a combination like x plus 2. Think of variables as named containers and assignments as the way we fill or update those containers. Once you understand this pattern, you'll be able to build your program one step at a time by assigning and updating variable values as needed. Essential C programming concepts. Expressions, variables, and functions by the programming professor. Here's what we'll cover in this video. We'll start with variables, assignments, and identifiers, how you store and name data in memory. Then, we'll explore arithmetic expressions and build example programs that show how math works in C. Next, we'll look at floating point numbers and scientific notation, critical for handling decimal values. From there, we'll move into constants and math functions that let you reuse values and perform advanced calculations. We'll also cover division, modulo, and type conversions, then dive into binary representation, character data, and strings. You'll learn how to prevent integer overflow, when to use unsigned types, and how to generate random numbers. Next, we will look at program input and output using printf and scanf, and finish by discussing key debugging strategies and clean code style. If you're serious about mastering C, this outline is your roadmap. Finally, we'll wrap it all up with a summary and takeaways so you leave confident in these core concepts. Let's explore how variables and assignments work together in C. A variable is simply a named container that stores a value. You can think of it like a labeled box in memory where your program keeps data. For example, a variable named x or numPeople might hold a value like 5 or 100. To store a value in a variable, we use an assignment statement, such as x equals 5. This means the value 5 is placed into the memory location, labeled x. That value stays there until it's reassigned later. Every assignment statement has a variable on the left-hand side and an expression on the right. The right side is evaluated first, and the result is then assigned to the variable on the left. That expression could be a literal like 5, another variable like y, or a full calculation like x plus 2. Understanding this flow is essential to building logic and keeping track of values in your program. Sometimes you'll see a variable appear on both the left and right sides of an assignment statement. This is completely valid and actually very common. In C, the equals sign means assignment, not equality. So, when you write x equals x plus 1, you're not claiming x equals x plus 1. Instead, you're taking the current value of x, adding 1, and storing that new value back into x. If x starts as 6, after this statement it becomes 7. You've updated it, or as programmers often say, you've incremented it. This is a core technique used in loops, counters, and many algorithmic processes. It's important to recognize that this does not create a circular or infinite relationship. Only the right-hand expression is evaluated, and the left-hand variable is updated afterward. You'll also see similar patterns like x equals x times 2 or x equals x minus 1, which follow the same logic. Mastering this pattern gives you dynamic control over variable state throughout your program. Before you use a variable, you must declare it. A variable declaration tells the compiler what kind of value the variable will hold and gives it a name. For example, int userAge declares a variable named userAge that can store an integer. Behind the scenes, the compiler reserves a memory location for that variable, maybe location 97, though the exact address doesn't matter to you. What's important is that userAge now has a space in memory where a value can be stored. When you assign a value to it later, like userAge equals 22, that value is stored at the memory address associated with the variable. When you read from the variable, C pulls that value back from memory. The key rule here is that the variable must be declared before it's used. Without a declaration, the compiler doesn't know how much memory to allocate or what type the variable should be. Assignment statements are how we store values into variables once they've been declared. The syntax uses the equals operator, with the variable on the left and an expression on the right. For example, numapples equals 8 assigns the value 8 to the variable numapples. The right-hand side is always evaluated first, then the result is stored into the variable. That right-hand side can be a literal number like 80, another variable like numapples, or a more complex expression like numapples plus 1. You can also include parentheses to control the order of operations, as in 2 times open parentheses, numapples minus 1 closed parentheses. A number like 80 written directly into the code is called a literal. Assignment statements are the building blocks of logic flow in C. They allow you to compute, store, and reuse values dynamically as your program runs. Although it's optional, it's a good habit to initialize variables with a starting value at the time of declaration. For example, int maxScore equals 100 creates a variable named maxScore and immediately assigns it the value 100. This helps avoid bugs where a variable is used before it's been assigned. It's also very common to use the same variable on both sides of an assignment. For example, numItems equals numItems plus 1 increments the current value by 1. If numItems was 5, it becomes 6. The program evaluates the right-hand side first, reading the current value of numItems, adding 1, then stores the result back into numItems. This pattern is essential for tracking changes in loops and counters. It's worth noting that while you can update a variable's value after declaring it, initializing right away helps with both clarity and safety in your code. A very common error, especially for beginners, is trying to read from a variable that hasn't been assigned a value yet. When you declare a variable like int x, but don't initialize it, its memory location could contain anything. It's unpredictable. While some systems may default to 0, that's not guaranteed. A program might appear to work on one computer, but fail on another just because of this uninitialized value. That's why initializing variables at the start is such a strong habit to build. Another common mistake is writing an assignment statement in reverse. For example, writing 9 equals beans count instead of beans count equals 9 that will trigger a compile time error because the left-hand side must be a variable, not a literal. However, accidentally reversing variable names, like numdogs equals numcats when you meant the opposite, will compile fine, but lead to subtle, hard-to-find logic bugs. Careful variable usage helps avoid these traps. Let's talk about identifier rules in C. An identifier is simply the name you assign to things like variables and functions. To be valid, an identifier must start with a letter or underscore and can only contain letters, digits, or underscores. For example, userAge and underscore total are valid names. However, 3 dogs is not because it starts with a digit. Identifiers in C are also case-sensitive, so numcats and numcats are treated as 2 separate variables. It's also important to avoid using reserved words, which are special keywords in C like int, return, or while. These words have predefined meanings in the language and cannot be used as identifiers. Most code editors will highlight reserved words automatically to help you avoid mistakes. Choosing valid Descriptive identifiers will make your code easier to read, debug, and maintain. Follow these basic rules, and you'll avoid many common pitfalls when naming variables. Now let's talk about style, specifically naming style. While many different styles are technically valid, teams often follow specific naming conventions to keep code consistent and readable. Two common conventions for naming variables are camel case and underscore separated. In camel case, you start with a lowercase letter and capitalize the first letter of each new word, like numapples or people on bus. In the underscore style, all letters are lowercase, and words are separated with underscores, like numapples. Neither is right or wrong, but consistency is key. You should also make your variable names meaningful and avoid abbreviations, unless they're commonly understood, like num for number. For example, average age is much more descriptive than just age or A. On the flip side, names that are too long, like average age of UCLA graduate student, can be hard to read and maintain. Striking a balance between clarity and brevity makes your code more professional and user-friendly. Let's take a closer look at the reserved words in C. Also called keywords, these are special words that are built into the C language and have predefined meanings. Examples include int, char, if, return, while, and many more. Because they are part of the core syntax, you cannot use them as names for your variables or functions. For instance, trying to name a variable while or return would confuse the compiler and result in an error. There are over 30 reserved words in standard C, covering data types, flow control, storage classes, and more. Most development environments will automatically highlight these keywords to make them stand out in your code. While you don't need to memorize them all at once, it's important to recognize that these words are off-limits when choosing identifiers. As you write more programs, you'll naturally become familiar with the most commonly used ones. In C, expressions are used to perform calculations and evaluate to a result. These expressions are made up of variables, literals, operators, and sometimes parentheses. A simple example is 2 times x plus 1, which adds 1 to x and multiplies the result by 2. This kind of expression often appears on the right-hand side of an assignment statement, like y equals 2 times x plus 1. Here, y is assigned the result of that expression. The number 2 is a literal. It's a fixed value written directly into the code. An operator like plus or asterisk performs a built-in math operation. Operators can also be used in more complex combinations, and you can use parentheses to control the order of operations, just like in standard math. Understanding expressions is critical because they form the core of how calculations, logic, and assignments are performed in your programs. Now that we've covered expressions, let's look at operator precedence, how C determines which part of an expression to evaluate first. Just like in regular math, operations in C follow a specific order. Expressions inside parentheses are evaluated first. Then, negation using unary minus comes next. After that, multiplication, division, and modulo operators are evaluated. Finally, addition and subtraction are performed. If multiple operators have the same precedence, like multiplication and division, they're evaluated from left to right. For example, in the expression 3 plus 2 times x, C will evaluate 2 times x first, then add 3. Parentheses can override precedence to ensure the correct order. If you want to force addition first, write it as open parenthesis 3 plus 2 closed parenthesis times x. Mastering precedence helps you avoid bugs and ensures your programs do the math you expect. Always use parentheses when in doubt. They make your code easier to read and understand. Let's look at a practical example of using expressions to compute something meaningful. Suppose you're writing a program to calculate the total cost of leasing a car. You'll ask the user for 3 inputs: the down payment, the monthly payment, and the number of months in the lease. Then you compute the total cost by multiplying the monthly payment by the number of months and adding the down payment. The expression looks like this. Total cost equals down payment plus open parenthesis payment per month times num months closed parenthesis. This one line uses an expression to combine user-provided values into a final result. After calculating, the program prints the total cost. This example shows how expressions allow your program to do real work, turning input into output through mathematical logic. Consistent formatting is key when writing readable and maintainable code, especially when working with math expressions. One style guideline is to include a single space around operators like plus, minus, asterisk, and forward slash. For example, write num items space plus space 2 instead of num items plus 2. It makes the code easier to scan and understand. One exception is when using the minus sign as a negative operator, like x coord equals negative y coord. This is called unary minus, and there's no space between the minus and the variable. Another useful tool is compound operators. These are shorthand versions of assignment expressions. For instance, userage plus equals 1 is the same as writing userage equals userage plus 1. Other compound operators include minus equals, asterisk equals, slash equals, and percent equals. One final reminder, don't use commas in integer literals. Writing 1000 with a comma will cause an error. Instead, write 1000. Clean formatting reduces confusion and prevents common bugs. Now let's talk about floating point numbers in C, which are used to represent real numbers with decimal points. In C, a double variable is typically used for floating point values. For example, you might declare double miles traveled to hold a value like 98.6 or 0.0001. A floating point literal is any number that includes a decimal point, even if the decimal is 0, like 1.0 or 0.0. Good practice is to always include a digit before the decimal to avoid confusion, so write 0.5 instead of 0.5. To read or write a double value, you use the format specifier %lf in scanf or printf. This stands for long float and is specific to double values. Using floating point variables correctly allows your programs to handle a wide range of real-world measurements and calculations that go beyond whole numbers. When choosing between int and double, think about the kind of value you're trying to store. Use an int for values you count, like number of people, pizzas, or steps. These are whole, countable items. Use a double for things you measure, like temperature, weight, or distance, which can include fractions. For example, if you want to calculate the average number of cars per household, you'd need a double because the answer might be 2.3. One important note: many programmers recommend not using floating point types to represent money. For instance, representing $14.53 as 14.53 could lead to rounding errors. Instead, you can store money in cents using an integer, like 1453, or use integers for whole dollar values when cents aren't needed. Picking the right type ensures your data is represented accurately and prevents errors, especially when precision really matters. What happens if you divide a floating point number by 0? Unlike integer division, which crashes the program with a runtime error, floating point division in C doesn't cause an immediate crash. Instead, it returns a special value. If you divide a non-zero number by 0, C returns int for positive infinity or negative int for negative infinity, depending on the sign. If both the dividend and divisor are 0, the result is nan, meaning not a number. These values can still be stored in variables and printed using printf, which will display inf, negative inf, or nan. While this behavior avoids crashing, it can lead to logical errors if you're not expecting it. so it's still important to check for divide by zero cases in your calculations. Floating point numbers often have a lot of digits after the decimal point, and while that can be useful for precision, it's usually more detail than you need in everyday output. For example, you may only want to show 2 decimal places, especially if you're displaying something like a dollar amount or a measurement. C allows you to control this using a format string in printf. The format %2 LF tells printf to show exactly 2 digits after the decimal. So printf %2 LF, my float, would display the number rounded to 2 decimal places. It's important to note that this doesn't change the actual value stored in memory. It only changes how the number is displayed. This technique is helpful for simplifying output and improving readability, especially in user-facing programs. Sometimes, we need to work with very large or very small numbers, like the number of atoms in a sample or the size of a microscopic object. In C, these are often written using scientific notation. For example, the number 6.02 times 10 to the 23rd power can be written as 6.02 E23. The E stands for exponent, meaning times 10 to the power of. Similarly, a small number like 0.001 can be written as 1.0 E-3. This makes it easier to write and read extremely large or small values without typing out a long string of zeros. Good practice is to always start the number with a non-zero digit, like 1.0 E-3 instead of 0.1 E-2, to avoid confusion. Scientific notation is a powerful tool for working with real-world data that spans a wide numerical range. A good habit in programming is to avoid hard-coding literal values directly into your code. Instead of writing something like new price equals org price minus 5, it's much clearer and more maintainable to write new price equals org price minus price discount. That way, it's obvious what the value represents. To prevent that constant value from being accidentally changed later in the code, you can declare it using the const keyword, like const int price discount equals 5. This tells the compiler that the value is fixed, and any attempt to change it will result in an error. It also signals to other programmers that this variable is a constant. In terms of naming, the common convention is to use all uppercase letters with underscores between words, so constants stand out clearly in the code. This simple practice boosts readability and protects your constants from unintended changes, especially in larger programs or teams. Sometimes your program needs to do more than just basic math, like computing a square root or a power. In C, you can use math functions from the standard math library, which provides about 20 common operations. These are called functions, and they work by passing input values, called arguments, into the function call. For example, if you want to calculate the square root of a number stored in area square, you would call sqrt of area square. That result can be used in an assignment, like side square equals sqrt of area square. Function calls always use parentheses, even if there's only one argument. Functions let you perform complex calculations in a clean, readable way without having to write the math logic yourself. Just don't forget to include the math library with #include math.h at the top of your program, or the compiler won't know what sqrt means. Let's take a look at a few of the most common math functions available in C's standard math library. First is sqrt of x, which returns the square root of x. So sqrt of 9.0 returns 3.0. Then there's pow of x, y, which raises x to the power of y. For example, pow of 6.0, 2.0 evaluates to 36.0. You also have fabs of x, which returns the absolute value of a floating point number. So fabs of negative 99.5 becomes 99.5. These functions make it easy to handle complex mathematical operations in just one line of code. There are also others like logarithms, log, log base 2, log base 10, exponential growth with exp, rounding functions like ceil and floor, and trigonometric functions such as sine, cosine, and tangent. You don't need to memorize them all now, but know that these are powerful tools available anytime your program needs math beyond basic arithmetic. In C, you can even nest one function call inside another. This is known as a function call as an argument. It's a convenient way to compute intermediate results on the fly. For instance, let's say you have a variable x, and you want to raise 2 to the power of x, y plus 1. You can write that as pow of 2.0, pow of x, y plus 1. Here's what happens. Pow of x, y is evaluated first and returns a value. Then you add 1 to that result. And finally, pow of 2.0, ... uses that sum as the exponent. This nesting allows you to express complex calculations compactly, but it's important to keep your code readable. Use indentation or break it into multiple lines if it gets too hard to follow. Remember, clarity always beats cleverness when it comes to writing good, maintainable code. Understanding how division works in C is essential, especially when it comes to integer division. When both operands in a division operation are integers, C performs integer division, meaning it throws away any remainder and only keeps the whole number part. So 7 divided by 2 becomes 3, not 3.5. But if at least one operand is a floating point number, then C will perform floating point division and keep the decimal. For example, 7.0 divided by 2, or double, 7 divided by 2 will result in 3.5. Another critical rule: never divide by 0. In integer division, trying to divide or use modulo with 0 will cause a runtime error and terminate the program. This is called a divide by 0 error, and it's a common beginner mistake. Always check that the divisor isn't 0 before performing division to ensure your program runs smoothly and safely. The modulo operator, written as the % symbol, is used to get the remainder of an integer division. It's a powerful and frequently used tool in C programming. For example, 23 modulo 10 equals 3, because 23 divided by 10 gives a quotient of 2 and a remainder of 3. Some more examples. 9 modulo 5 results in 4, 70 modulo 7 gives 0, and 1 modulo 2 gives 1. But here's something to watch out for: both operands must be integers. You can't do something like 10 modulo 4.0. That would result in a compile time error, because the modulo operator doesn't work with floating point numbers. Modulo is especially useful for checking divisibility, wrapping values in loops, and working with digit-based calculations, such as getting the last digit of a number. You'll see modulo come up often in logic, especially when working with conditionals, counters, or arrays. Let's look at some common uses of the modulo operator. One major application is generating random numbers in a fixed range. If you use rand modulo 10, you'll get a number from 0 to 9, 10 possible values. Want 0 to 50? Use rand modulo 51. If you want a range starting at a number other than 0, you just add an offset. For example, parenthesis rand modulo 9 parenthesis plus 1 gives a range from 1 to 9, and parenthesis rand modulo 11 parenthesis plus 20 gives values from 20 to 30. Another use is digit extraction. For example, to pull digits from the number 927, you can use modulo and division operations to isolate the ones, tens, and hundreds digits. You can also use modulo to isolate parts of large numbers like phone numbers. These techniques are useful in countless real-world problems, from formatting output to solving algorithm challenges. When performing calculations in C, you often mix integers and floating point numbers. This leads us to the concept of type conversion, when a value of one type is automatically or manually changed to another. In many cases, C handles this automatically. For example, if you write 0.504 times numbirths, and numbirths is an integer, the compiler implicitly converts it to a double so it can perform floating point multiplication. This is called implicit conversion. Arithmetic operators will promote types as needed, and in assignments, the value on the right side is converted to match the variable type on the left. So if you assign a double to an int, the fractional part will be dropped. Likewise, assigning an int to a double simply adds a 0.0. Understanding these conversions is crucial to writing code that produces accurate results, especially when combining types in mathematical expressions. Sometimes, automatic type conversion isn't enough, or isn't what you want. That's where typecasting comes in. Typecasting allows you to explicitly convert a value from one type to another using a simple syntax. For example, double 7 turns the integer 7 into a floating point number. This is especially useful in division. If you write int result equals a, divided by b where both a and b are integers, you'll get integer division. But if you want a decimal result, you can cast one of the operands. Result equals double a/b. The division will now be treated as floating point. You can also cast values the other way, from double to int, but be aware that you'll lose any fractional part. Casting gives you precise control over how values are interpreted and used, especially when mixing data types in calculations. While we usually think in terms of base 10, a computer stores and manipulates data using base 2 or binary. That's because each bit in memory is either 0 or 1. When you declare a variable like int x equals 212, the compiler actually stores that number in binary. For example, the decimal number 212 becomes 110101000 in binary, meaning 1 times 128 plus 1 times 64 plus 0 times 32, and so on. This binary representation is how the processor reads and processes numbers. Since every variable is stored in memory using a fixed number of bits, like 32 or 64, the range of values you can store is limited. This is why understanding binary matters, especially when you start working with low-level operations, bit manipulation, or need to optimize memory usage. Even though you'll mostly think in decimal, it's good to know how your code translates under the hood. In base 2, each digit is a bit that can only be 0 or 1, and each position in a binary number represents a power of 2. Just like in base 10, where each digit represents powers of 10, like 1s, 10s, 100s, in binary you have 1s, 2s, 4s, 8s, and so on. For example, the binary number 1101 represents 1 times 8 plus 1 times 4 plus 0 times 2 plus 1 times 1, which equals 13 in decimal. When you write a number like 212 in your C program, the compiler automatically converts it to binary before storing it in memory. For 212, the binary representation is 1101010. This means the computer stores it as 1 times 128 plus 1 times 64 plus 0 times 32 plus 1 times 16 plus 0 times 8 plus 1 times 4 plus 0 times 2 plus 0 times 1. Understanding how numbers are represented in binary gives you better insight into how data is stored, processed, and sometimes limited by your machine's architecture. C also allows you to store individual characters using the char type. A char variable holds a single character, like m, and is declared with a line like char mychar. You assign it using single quotes, mychar equals m. When printing characters with printf, use the %c format specifier, so printf. %c, mychar, will print the character stored in mychar. Similarly, to read a single character from user input, you use scanf. %c, ampersand mychar, but here's a tip. Include a space before %c to make sure it skips any leftover whitespace like newlines or spaces. Unlike integers or floating point values, characters represent letters or symbols, but under the hood, they're still stored as numeric codes. You'll learn more about that shortly, but just remember, %c is for character output and input, and characters use single quotes, not double. Although characters are written as letters or symbols, they're actually stored as numbers. For instance, the character A is stored as the number 97. This is part of a standard encoding system called ASCII, where each character corresponds to a specific numeric value. When you use %c in printf, it prints the character version of that number. But if you used %d instead, it would print the numeric ASCII value. This mapping enables programs to perform comparisons, sorting, and transformations on characters using simple arithmetic. For example, you can compare A less than Z, or even increment a character to go to the next one in the alphabet. The ASCII table includes letters, digits, symbols, and special control characters. While you don't need to memorize it, being aware of ASCII will help you debug and understand how characters are stored and manipulated. Some characters, like newlines or tabs, aren't visible in your code output but still affect formatting. To represent these, C uses escape sequences, special two-character codes that start with a backslash. For example, \n adds a newline, and \t inserts a tab. If you want to print a quote or a backslash itself, you also need escape sequences: \single quote, \double quote, and \\. These are especially important in output formatting and when writing strings that contain special characters. For example, if you want to assign a single quote character to my char, you'd write my char equals \single quote, and to assign a backslash, you'd use my char \\. Without the backslash escape, C would get confused trying to interpret the character literal. Learning these escape sequences is essential for working with formatted text and avoiding syntax errors when special characters are involved. In C, a string is a sequence of characters stored as a character array. Unlike int or double, there's no built-in string type. You have to use an array of char. A string literal is written inside double quotes, like hello or 42. This is different from a character literal, which uses single quotes and can only hold one character. A string can include letters, numbers, spaces, and symbols like $sign or %, and when you print one using printf, you use the %s format specifier. For example, printf, hello, simply prints the string hello to the screen. Strings are incredibly useful in programs that require names, labels, messages, or any form of text output. Understanding that strings are actually arrays of characters is important because it means strings have fixed sizes, and special rules apply when assigning or comparing them, which we'll explore further in upcoming slides. In C, strings are stored as character arrays. To declare one, you define an array of char with a set size. For example, char first name 50 declares space for a string with up to 50 characters. It's important to use square brackets, not parentheses, to specify the array size. While C treats character arrays as strings, it's not a built-in string type like in some other languages. Also, unlike numbers, you can't use the equals operator to assign one string to another or to assign a literal string to a variable after it's declared. For that, you use a function called strcpy from the string.h library. It copies each character from one string into another. So strcpy, str1, str2 copies the contents of str2 into str1, as long as str1 is large enough. One exception is when initializing a string at declaration. For example, char first month 8 equals January works because the compiler handles the character copying. This also automatically adds the special null character, \0, at the end to mark the end of the string. Now, when it comes to reading a string from user input, scanf, %s, user string is commonly used. This function reads characters from input until it encounters a whitespace character like a space, tab, or newline. It skips any leading whitespace automatically and stops reading at the next one. One important thing to remember is that when reading a string using scanf, you do not use an ampersand before the variable name. That's because a character array already stores the memory address of its first element. Beginners often make two opposite mistakes here: forgetting the ampersand for integers or characters, or mistakenly adding it for strings. For strings, just pass the array name directly. So you'd write scanf, %s book title, not ampersand book title. This distinction between value types and address types is crucial in C, and becomes even more important as you move into functions and pointers. A limitation of scanf, %s, is that it stops reading at the first whitespace. That means if a user enters a name like Franklin D. Roosevelt, only the word Franklin will be stored. This is a problem when your string needs to include spaces, such as for full names, addresses, or full sentences. Unfortunately, handling whitespace in strings using scanf is tricky and not something we tackle right away. A better approach for reading full lines of input, including whitespace, is to use functions like fgets, which we'll cover in a later section. For now, just remember that scanf, %s, works for single words, and it will cut off the input at the first space or newline character. This is a common source of confusion, so don't worry, you're not alone in bumping into it early on. Now let's talk about integer overflow. Every variable in C is stored using a fixed number of bits, and that limits how large a number it can hold. For example, a typical int uses 32 bits, which allows it to store values up to about 2 billion. If you try to assign a larger value, like 4,294,967,297, it causes an overflow. The result: the high-order bits get chopped off, and you're left with an incorrect value, often something completely unexpected. For example, if the 33rd bit is dropped, the number stored may wrap around and appear as a small value like 1. This can lead to serious bugs, especially if your program relies on accurate counts or calculations. It's essential to be aware of this limit and choose larger types, like long, when you expect values to exceed that boundary. But even long has limits, so understanding overflow is key to writing safe, robust code. To help prevent overflow, you can use the long type, which provides at least 64 bits and supports much larger values, up to over 9 quintillion. But be careful, even long can overflow if you push it far enough. Fortunately, most compilers will warn you when a literal constant is too large for a variable type. For example, GCC might say, warning, overflow in implicit constant conversion. Microsoft's compiler might show truncation of constant value. These warnings aren't syntax errors, so the program will still compile, but the results may be wrong. Always take these warnings seriously. A common mistake is not in the final result, but in the intermediate calculation. For example, if you add together 3 int values near 1 billion, the sum might exceed the int limit even though the average, after dividing by 3, would be fine. Rearranging the math, like dividing each value before summing, can sometimes avoid overflow. Understanding how operations are evaluated helps you avoid subtle, hard-to-find bugs. C provides several integer types to give you control over memory usage and number range. While int and long are commonly used, other types like char, short, and long are also available. Each type has a specific size in bits, and that determines the range of numbers it can represent. For example, a char typically uses 8 bits and can store values from -128 to 127, while a short uses 16 bits, allowing values from -32,768 to 32,767. On most systems, an int is 32 bits, with a range of roughly -2.1 billion to +2.1 billion. If you need to store even larger values, long gives you 64 bits and a massive range up to over 9 quintillion. Understanding the size and range of each type is essential for choosing the right one, especially when dealing with large data sets, memory limits, or calculations that must be precise. Let's talk about how these integer types behave in real programs. By far, the most commonly used type is int. While the C standard says it must be at least 16 bits, it's 32 bits on most modern systems. Similarly, a long is usually 32 bits, but on some systems, it can be 64. If you know your program needs to handle values above 2 billion, you'll want to use long, which is guaranteed to be at least 64 bits. When printing or reading a long, use the %LLD format specifier in printf and scanf. Now here's something C doesn't make easy. Formatting numbers with commas, like printing 8 million, requires custom code. Finally, beware of common user input errors. If your program expects a number, but the user enters a string, scanf might behave unpredictably or even crash. Validating user input and choosing the right type helps prevent bugs and keeps your program running smoothly. Floating point types allow you to represent real numbers with decimal points. In C, you have two common options, float and double. A float typically uses 32 bits, while a double uses 64 bits. That extra space gives double a much wider range and significantly more precision, up to about 16 significant digits, compared to just 7 for float. This is why most programs use double by default. Internally, these values are stored using a sign bit, exponent, and mantissa, but those details are abstracted away from you. Still, you should know that floating point values can overflow too. If you assign a value larger than the maximum for a double, the result will be stored as infinity, not a valid number. Also, because of their fixed precision, very long decimal values may be truncated. So be mindful of precision and overflow when working with floating point values. In addition to the standard sign types like int and long, C also provides unsigned versions of these types. Unsigned integers can only store non-negative values, 0 and up. Because they don't need to reserve a bit for the sign, they can store a wider range of positive numbers. For example, an unsigned int can store values up to about 4.29 billion, compared to a signed int's max of around 2.14 billion. This makes unsigned types useful in cases where you know a value will never be negative, like a person's age, a file size, or an index in an array. C supports several unsigned types: unsigned char, unsigned short, unsigned int, unsigned long, and unsigned long. Each has a defined size and corresponding maximum value. However, be cautious. Mixing signed and unsigned types in operations can lead to tricky bugs. Use unsigned types purposefully, and only when you're certain negative values are not possible. Sometimes, programs need to generate random numbers for games, simulations, or security purposes. In C, the standard function for doing this is rand, which returns a pseudorandom integer between 0 and a system-defined constant called rand_max. This maximum is machine-dependent, but it's guaranteed to be at least 32,767, and often it's much larger, like 2 billion. Most of the time, you don't need the full range of values rand can provide. Instead, you want a number in a specific range. That's where the modulo operator comes in. For example, rand%10 gives you a number from 0 to 9. It's a quick way to narrow the random output down to a usable range. But remember, the result always starts at 0 and ends at 1 less than the divisor. Often, you'll want a random number that starts at a number other than 0, say 10 to 15 or minus 20 to 20. To do that, start by figuring out how many total values are in the range. Then use rand%n to generate one of those values and add an offset. For example, to get a number from 10 to 15, you calculate rand%6 to get a number from 0 to 5, and then add 10. So the formula becomes rand%6 plus 10. This technique works for any inclusive range. Just subtract the min value from the max, add 1 to get the total number of values, and use that in the modulo. Then add the min value back on. It's a simple pattern but incredibly useful in game design, simulations, and random testing. Just be sure the range and offset match, or you could get unexpected results. One important thing to understand is that the values generated by rand are not truly random, they're pseudorandom. That means they follow a deterministic pattern that only appears random. In fact, every time you run a program that calls rand, you'll get the same sequence of numbers unless you change the seed. By default, the seed value is 1. If you want different sequences every time the program runs, you need to call srand with a unique seed. A common technique is to use the current time with srand, time null, which changes the seed based on how many seconds have passed since January 1st, 1970. This gives you fresh results on every run. But be careful, srand should only be called once, and always before the first call to rand. If you call it multiple times or too late in the program, the sequence may repeat unexpectedly. The printf function is one of the most commonly used tools in C, and it's how you display output to the screen. You include it by adding #include standard io.h at the top of your file. The first argument to printf is a format string, which can include regular text and format specifiers, special placeholders that insert values. Each format specifier begins with a % symbol, followed by a code that tells C what kind of value to print. For example, %d is for integers, %c for characters, %f or %lf for floating point numbers, and %s for strings. You can use multiple specifiers in a single format string, as long as you provide matching values as arguments after the string. It's a flexible system that allows you to control exactly how your output is formatted. Now that we've introduced how printf works, let's walk through some of the most common format specifiers you'll use when displaying different types of values. Each specifier starts with a %sign, followed by a letter that represents the data type. For characters, use %c. For integers, %d is your go-to. It works with standard int variables. If you're using a short, use %hd. For long, use %ld, and for long, it's %lld. Unsigned versions of these types also have their own specifiers, like %u for unsigned int, %lu for unsigned long, and so on. For floating point numbers, use %f for float and %lf for double. If you're printing strings, use %s, which prints characters up to the null terminator. Finally, if you ever want to print an actual % sign, use %%. Matching the right specifier with the right variable type is critical. Otherwise, you'll get incorrect output or strange behavior. This table of format specifiers will be something you refer back to often, especially as your programs start handling more diverse data. Let's look at how to use format specifiers with printf to produce clean, readable output. Suppose you want to print a sentence that includes a variable, like total people known. You could write printf, %d people /n, total people known. The %d tells printf to expect an integer, and it replaces that placeholder with the value stored in the variable. So if total people known is 5, the output would be, 5 people. You can do the same with other data types, %c for characters and %s for strings. You're not limited to just one value. You can include multiple format specifiers in a single printf call. For instance, to show rainfall data, you might write printf. Daily rainfall in past %d days was %lf inches/n, num days, avg rainfall, where %d and %lf are replaced by their corresponding variables. The arguments after the format string must match the order and types of the specifiers. This approach lets you display detailed, structured output in one step. And if you need to print a literal % sign, like in 9% interest, use %% inside the format string. It's this mix of clarity and flexibility that makes printf such a powerful tool. Now let's talk about the scanf function, which is used to read input from the user. Just like printf, it uses a format string to specify the expected data type, %d for integers, %lf for doubles, and so on. The key difference is that scanf requires the address of the variable you're reading into, so it knows where to store the value. For example, if you declare int numFriends, you'd write scanf, %d, &numFriends. The ampersand tells scanf the memory location of the variable. Forgetting the ampersand can lead to unpredictable behavior or crashes, which is a common beginner mistake. But strings in C work differently. They're stored as character arrays, and the array name itself already points to memory. So if you declare char book title 50, you would use scanf, %s book title, without the ampersand. Be aware that %s stops reading at the first whitespace, so something like C Programming Guide would only store C. We'll explore how to read full lines later, but for now, remember, use ampersand for numbers, not for strings. Debugging is a core skill in programming. It's the process of identifying and fixing problems in your code. Sometimes it's called troubleshooting, but the idea is the same. Figure out why your program isn't working as expected and fix it. This isn't something you do occasionally. It's a routine part of being a programmer, just like diagnosing is part of a doctor's job. The better you get at debugging, the more productive you become. You'll spend less time stuck and more time building working solutions. Debugging often involves tracing the logic of your code, printing variable values, and thinking carefully about what the program is doing at each step. It can be frustrating, but it's also incredibly rewarding when you solve a tough issue. In fact, learning how to debug effectively is one of the most valuable skills you'll develop as a coder. As you continue developing your programming skills, following consistent style guidelines will make your code easier to read, understand, and maintain, both for yourself and for others. One of the first areas to focus on is whitespace and formatting. A good rule is to put only one statement per line. For example, write x equals 25 and y equals x plus 1 on separate lines, not squished together. Group related statements together without blank lines, and use blank lines to separate logically distinct blocks of code. Use one space around operators like plus, equals, and asterisk, but not before semicolons. Also, avoid using tabs for indentation. Instead, indent your substatements with 3 spaces to keep everything consistent across different text editors. This kind of visual clarity makes your code much easier to follow and debug, especially when you revisit it later or collaborate with others. Even small formatting choices can make a big difference in how professional and readable your programs feel. Beyond whitespace, let's look at conventions for braces and naming. We use the K and R style for braces, where the opening brace appears at the end of the line, and the closing brace is aligned directly below the statement that opened it. For if-else structures, we will place the else on a new line. Always use braces, even if there's only one line of code in the block. It helps prevent future logic errors. For naming, use camel case for variables and function parameters, and capitalize function names like printMessage. Variable names should be descriptive, prefer num students over n or s. Constants should be written in all caps with underscores, like max height. Declare your variables early in a block and initialize them when possible. These naming and brace conventions will not only help your code look clean, but also align with what's expected in many professional coding environments. To wrap up this module, let's quickly review what we've covered. We've covered the foundational concepts of C programming that every beginner needs to understand. We started by learning how variables store data and why meaningful identifiers help make our code more readable. Then we looked at arithmetic expressions, which let us calculate and update values in our programs. From there, we explored data types, like int, double, and char, each used to store different kinds of information. We introduced constants, math functions, and type conversions, which allow you to build more complex and flexible programs. You also learned how to handle user input and display output using scanf and printf, along with format specifiers. We touched on binary representation, how overflow can occur, and the role of unsigned types. Strings were introduced as character arrays, with special handling for input and manipulation. We also covered how to use random number generation with rand and srand. And finally, we wrapped up with key debugging strategies and clean style guidelines, because writing readable, consistent code is just as important as writing code that works. Thanks for watching. Let me know in the comments if there are other topics you would like me to talk about. If you enjoyed this video, please like, share, and subscribe for more content on software engineering and technology. See you next time.